Hello and welcome to 4.5 Quantitative Data Analysis Techniques. Quantitative data is data that is expressed through numbers or data that can be transformed into usable statistics. Quantitative data is much more objective. The accuracy of it is far more clearer than qualitative data and tends to be more reliable. Quantitative data analysis also tends to be easier to discover patterns of behaviour or overriding themes. When organising and preparing data, there are four methods. These are using the range, using simple frequency distribution, using rank order distribution, and grouped frequency distribution. Data preparation and organisation is vital for research projects as it shows how the data can be separated and manipulated into manageable groups that can then be made into statistics and analysed. To begin with then, the range. The range is the difference between the largest and smallest number. To work out the range from a set of numbers, you get the largest number from the data and subtract the smallest number from it. The number you get is the range between the numbers. You would use the range in cases where there is not an anomaly number, as this can overly increase and decrease the range between the numbers. When numbers pulled from a data sample have a similar difference, this is when you would use the range. You would also use the range here to find out whether there are errors in the data, as the range can detect these errors and give an unrealistic range. This is when you know that there has been an error and the researcher can go back over the data and find out where they might have gone wrong. The example I've used here is data pulled from the sit and reach test. To find the range from this data, you find the highest number, which is 56, and the smallest number, which is 22. To work out the range, you should now find the difference between the two. The quickest way and easiest way to do this is by subtracting 22 from 56, which equals 34. This value is your range. Next up, simple frequency distribution. This is when you collect data and separate it by ranking the data into frequencies rather than showing more than one of the same number in the data. If 5 people have the same measurements for their biceps, the table divides them so that they are included in the frequencies after the measurements. To finish the simple frequency distribution, you have the cumulative frequency column at the end. This is where you add the frequencies together until the bottom row, where it should equal the amount of measurements originally made. Here in this example, we used skin fold calipers to test the excess skin on the triceps and biceps of the gymnast and measured in millimeters. There were various scores that were the same, and so they are placed into the same frequencies. The first row shows that there were 3 people that had the same measurements of 4 millimeters on their bicep. Rank order distribution is as simple as it means. From the data sample we collected, you then rank the numbers from the lowest to highest. In this example, we used thigh girth, which is measured in centimeters. From the measurements we got, you then rank the numbers in a table like so, starting with 34 as the lowest, all the way down to 63 being the highest. Finally, grouped frequency distribution. This is very similar to simple frequency distribution, as you collect data and then rank it into certain categories, then use a frequency column to see how many times that number, or in this case a group of numbers, repeat themselves. Grouped frequency distribution uses the same format as simple frequency, but instead of single numbers, it groups its numbers into certain decimals, as this data is normally so close together it cannot be separated without using the decimal place. It is most likely that when there are lots of different numbers recorded from the results, and not many people got the same results, this is why it's common for decimal numbers, as it is unlikely for people to get the same decimal place results. In this example, I've used the static sprint, which is measured in seconds and milliseconds, on a stopwatch. It's easy to use the static sprint as not many people got the exact same results but were separated by decimals. After you've collected the data, you start by putting the decimals in order and then find certain groups that they can be divided by. I've separated the numbers by 0.2 each time. Presenting data. There are 6 possible ways to present the data. These are through different graphs and tables which represent data in the most appropriate and professional way. The 6 ways to present data are through a line graph, scatter plot graph, a table, a box and whiskers graph, a histogram, and a bar chart. To begin then, the line graph. A line graph is usually made to compare bits of data. Each data result is marked on the graph, and when they are all marked down, they are all connected with a line. Both groups of data should have a line to show where the results are plotted. The researcher should then be able to see how the results change over the period of time given. The lines on the graph should show a clear comparison in the data. Each result is made into points, and when all the points have been noted, they can see how the results change over that period of time. The smaller vertical lines on the graph is the standard deviation of the results. This shows how much the results deviate from one another. If the line on the graph of the standard deviation overlaps, then this suggests that there is a larger difference in between the results. A histogram. A histogram is a special form of bar chart where you display the quantitative data along the x-axis and the frequency of that variable on the y-axis. A histogram represents continuous rather than discrete categories. It shows the frequency of how often each different value in a set of data occurs. For example, if the frequency of 3 people scored the same result on the high jump would be 3, and this should be shown in the height of the histogram. The example we used was from the flying sprint and categorized the scores using grouped frequency to reduce the amount of categories we had. The largest frequencies are clearly seen in the category of 1.46 to 1.75. This means the largest amount of people scored in between those scores. Table. A table is just an effective way of presenting data when you want to show how individual information varies when it is measured at different points. As you can see by this example, each column has its own mean, standard deviation, median, mode, maximum, minimum, and the range. This helps people to quickly identify the dispersion of the data. We use the table to work out the standard deviation, median, mode, maximum, minimum, and range of 3 sets of data, which were the static sprint, standing vertical jump, and also the flying sprint. Next up is the box and whiskers. A box and whiskers chart consists of boxes that represent the interquartile range of the data, but also the median and the mean of the data. The whiskers are the lines either side of the boxes and are used to represent the largest and smallest values in the data set. The data that is not included in the data set is presented as individual points and are called outliers. Here in this example we were comparing resting blood pressure of systolic and diastolic. Next was a scatter plot graph. A scatter plot displays all data as single points on the graph. It shows the relationship between pairs of quantitative measurements made for the same objective or individual comparing these results. From this you can then identify from the dots whether there is any systematic or causal relationship between the two measurements. With our example, this is not the case as they are all kind of plotted around the graph and you wouldn't be able to do a line of best fit. We compared the relationship between height of the participants and their sit and reach scores, which there was no relationship. The principles of the bell shape. All normal distributed data will have something to this bell-shaped curve here. The top of the curve or bell represents the most probable event in the data, whilst the rest of the data is represented in the curves sloping either side of the peak. The rest of the data either side of the peak is evenly distributed into standard deviation. The taller the shape of the bell means that there is a bigger standard deviation. The taller and thinner of the bell shape means that the most probable event in the data is small, whereas a larger bigger bell shows that the data is similar and there is a smaller level of standard deviation. The normal distribution curve typically has a greater range of data within the set of data as there is a wider spread through the whole graph. It will normally fall under, with the mean being the center point. You normally find that the rest of the graph will fall under -1 or +1 standard deviation, but can be more depending on the results that are used. However, it can occur where the distribution can be negatively skewed and is skewed to either the left or right if the scores recorded are more in the higher side of the scale, with the other scores being a lot lower. When the mean is greater than the median, which will always be greater than the mode, this is positively skewed and skewed to the right. The most common number of the data will always be at the peak of distribution, as this is where the majority of the data will be. The mean will be at the tail of the curve, as this is the average for the whole data, and the median will be in the center of the curve, as this is where the middle number will be located. Outliers in data. So when presenting data, there might be outliers in the data that cause the presentation to look skewed or incorrect. So in order for the presentation to look relevant and correct, there are two methods for removing and sorting data so that it is manageable. These are trimming and windsoring. Trimming is removing numbers from the data that are anomalies. For example, if you collected data and most of the scores collected were similar and the difference between them was also similar, this would be okay and easy to present. But if there was one number that was much larger or much smaller than the rest of the data, this would be removed so that the data can be represented with ease. Windsoring is modifying the most legitimate anomaly of the data to the nearest and most acceptable number there is. For example, the data collected will have a similar difference between them, and the anomaly or anomalies that will be seen will be changed to the nearest and most acceptable number. Descriptive statistics. There are several ways to collect statistics from the data you've just presented. These are central tendency, which is the mean, median, the mode, and also dispersion. This is the range, interquartile range, and standard deviation. The central tendency are numbers that describe what is typical of distribution and to cluster around its mean, median, or mode. The mean is when you add up all the numbers from the data and then divide that total by how many numbers there are. The value that is given is the mean of the data. A limitation to the mean is that if there are outliers or anomalies in the data set that you are given, then it will affect the mean, giving a value that would not be a representative of the data. The median is the middle number in the set of data given. A limitation of the median is that depending on the size of the data set, it would not be a correct representation of the data. This would be true when you have a large collection of data. The mode is a number that occurs most frequently out of the rest of the numbers. A limitation to the use of the mode is that there could be multiple values that are modal and therefore not appropriate to use. Dispersion is the act and process of distributing things, data, or people over a larger area. Here I explain three types of dispersion. These are the range, interquartile range, and standard deviation. The range, as previously explained, is when you get the largest number from the data and subtract the smallest number from it. The number you get is the range between the numbers. You would use the range as a form of dispersion when the numbers have a similar difference between them. If the data set you have has a large anomaly in it, then it will affect how the range is calculated. The interquartile range is the process of dividing a data set into 4 equal quartiles. These quartiles are the lower quartile, the middle quartile, or the middle value, the upper quartile, and the interquartile range. Here, in this example on screen, the lower quartile is 63, the middle value is 71, and the upper quartile is 77. To work out the interquartile range, the lower quartile range is taken away from the upper quartile. Here in this example, it is 77 take away 64, which leaves you with an interquartile range of 13. Standard deviation is a value that indicates how much every value deviates from the mean or average of the data. To calculate standard deviation manually, first you need to calculate the mean of the set of numbers from the data collected. The mean of these numbers is x in the formula. Then subtract the mean from each of the scores that you collected. This is x take away x in the formula. Then the answer you get from that, find the square root of it to cancel out any minus values. This is x minus x squared in the formula. Now that you've squared all the numbers, add them all up to equal a sum. The sum that it equals is the top half of the formula. To finish off the formula, divide the top sum by how many values there are, minus 1. This is n minus 1 in the formula. To finish the formula, what you need to do is square root the answer, and this is the standard deviation you get for the data set given. Inferential statistics. This is the decision tree which helps researchers decide which test is the most appropriate for the research they're doing. It's as simple as answering the questions it gives and following them down to the right tests you need. The dependent t-test. The dependent t-test involves two sets of testing, and so two sets of data, but from the same set of participants. The researcher will collect two sets of data. These will be pre- and post-intervention. This is to see if there has been a difference from the intervention. The intervention could be stretching an energy product of some sort, or even learning a better, more efficient technique. To be able to complete this equation, you need the difference in the participants' scores all added up, the difference in the participants' scores squared, the number of participants minus 1, and the pre- and post scores. Once the equation has been completed, you then need to work out the critical value. To do this, find your n minus 1 value, which is 5. On the right hand column, move downwards until you reach 5, then move across and under 0.5, as this is our level of significance for a two-tailed test. The value that we reach when across and under these two values is 2.571, and this is our critical value. Then to work out the level of significance, you have to see whether the calculated value is smaller than the critical value, as this means there is no significance, but if it is bigger, then there is significance. As our calculated value was 9.91 and our critical value was 2.571, our study is significant as the calculated value is larger. The independent t-test. For the independent t-test, you have lots of data, but from two different groups, both completing the same activity. For both of these groups, you then need to find the standard deviation and the mean. These should be calculated and placed underneath each group in the table. For the equation, all you need is the number of participants from both groups and the standard deviation and mean for both sets. To work out the critical value, you add up the number of participants in both sets, which equals 20 and minus 2. This leaves us with 18. Move down the table of critical values down the left-hand side until you reach 18. And then move across to 0.5, as this is the level of significance for a two-tailed test. This leaves us with a value of 2.101, and this is our critical value. Our calculated value was minus 0.7, and therefore there is no significance as the calculated value is smaller than the critical value. Spearman's rank order test for relationship. In Spearman's test, you have two paired data sets from the same group of participants or participant. To begin with, the data should be ranked from lowest to highest in the columns of the Spearman's table. If some of the numbers in the dataset are the same, then they will be placed into brackets, and the actual rank of the number is placed to the right hand side of that number without any brackets. If there were two lots of 4s, then they would be shown like this: 4 in a bracket with a 7 on the other side, and the other one shown like this: the 4 in a bracket and the 8 on the other side. When you have ranked all the numbers from both data sets, you must find the difference between the two sets of ranks. Once the difference has been found, that number must be squared. These numbers are called the difference between the ranks squared. Then find out how many participants were involved and square that number, which should be clearly placed below. The difference between the ranks should always be 0, and the difference between rank squared should also be worked out. Here it is 187.5. Once all the boxes have been filled out and the calculations completed, you are then able to complete the equation. Once the equation has been completed, the critical value must be completed. You need to subtract the number of participants by 2, which leaves us with 8. You then move down the critical table values until you reach 8 and move across to 0.5. This leads you to a value of 0.74. This is our critical value. Our calculated value is minus 0.13, and so is smaller than the critical value, meaning there is no significance. Finally, Pearson's product movement correlation coefficient. For the Pearson's test, start by filling out the table. First, by squaring the results of the test completed by the participants. For example, if they achieve 5 centimeters on the sit and reach test, the x squared will be 25. Do this for both tests the participants completed. Once you have values for both x and y, add them together to create values for xy. Then for xy, add up all the values to create the sum of xy. Add up the values for x squared and the same for y squared. Add up the results of the participant scores for both tests, and then square this result to create a larger number for both tests. All the numbers you have added and squared should funnel down to 8 numbers at the bottom of the table, including the number of participants. These numbers should then be manipulated into the equation, and the equation should be worked out. Once the R value has been achieved, the critical value is next on the list of things to do. To be able to do this, find out how many participants you had, which was 8, and then minus 2. Then use the table of critical values to find 6, and move across to 0.05, which is the level of significance for a two-tailed test. This led us to the value of 0.7067, and this was our critical value. And using both values, you can see whether or not the testing was significant or not. Our calculated value was 0.837,899,1557, which means there is a significance difference, as the R value is above and bigger than the critical value.